Hello everybody and welcome back to another Algebra 1 video. Today we'll be finishing up lesson 5.4 extension with the last two special functions. We'll be starting off today's lesson with step functions. A step function also happens to be a piecewise function, meaning that it is made up of two or more linear equations, and they are defined by constant values over their domains. Now, if you have a linear equation that is equal to a constant value, like y equals 2 or y equals 7, you may recall that these represent horizontal lines. And if you see here on the right, you have an example of a step function. It's actually made up of several horizontal line segments. And how you get these shortened line segments is by graphing the domain. In this case, the domain is going to be in the format of a compound inequality. And if you recall anything from compound inequalities, you might remember that there's two different kinds. One of them is going to be connected with the word or, and those are going to be two different inequalities that are pointing in different directions. In this case, we're going to use the compound inequality connected with the word and those are two inequalities that are connected into one. So if you remember, there might be some recollection of this, but it would look something like this: y equals 2 if 1 is less than x is less than or equal to 2. So there are two different inequality symbols, and then your variable is resting in the middle. And so when you graph this, you're going to look for where y equals 2, for example, right here, and then you're going to graph y equals 2 where the domain is true. And I'll show you how that works once we get into an example, but the graph of a step function consists of a series of horizontal line segments, as you see here. And if you look at them, they kind of look like steps of a staircase, hence the name step function. Now we're going to transition into how to graph a step function. Looking at our example, we have f of x equals to this curly bracket that's called a brace, and inside the brace we see here that we have all our linear equations. In the case of step functions, we're graphing all horizontal lines in a specified domain. So I'll go ahead and get started by first graphing f of x equals 3 if 1 is less than x is less than or equal to 2. So remember that f of x is just a fancy way of writing y. So we're trying to graph the horizontal line y equals 3 in this domain. So we know we want to graph our horizontal line here at 3 on the y-axis, but you only want to graph it when 1 is less than x is less than or equal to 2. So go ahead and look for where that is on the x-axis. 1 is right here, so at your horizontal line of 3, since it is a less than symbol, you want to graph an open circle at 1, where x is equal to 1, so that would be right here. And then from there you want to do the same thing for x is less than or equal to 2. Since it's less than or equal to, you want it to be a closed circle at 2 on the x-axis, so that would be right here. And then remember, with compound inequalities, you just want to go ahead and connect your 2 points. So if you see here, this is your horizontal line, y equals 3, except it's only graph when 1 is less than x is less than or equal to 2. And from there you can go ahead and graph the rest of your linear equations. So next we have f of x equals 4 if 2 is less than x is less than or equal to 3. So we know we want a horizontal line at y equals 4, so right here. But our domain is 2 is less than x is less than or equal to 3. So you know you want to graph an open circle at positive 2, since this is a less than symbol. So our open circle would be right here. And then you can draw your other point at positive 3. And since it is a less than or equal to symbol, it's going to be a closed circle at positive 3, which would be right here. And from there, you can go ahead and connect those 2 points with a line. And there is your second linear equation graphed. Do it again for f of x equals 5 is 3. If 3 is less than x is less than or equal to 4, graphing our horizontal line at positive 5, which would be right here. But our domain is 3 is less than x is less than or equal to 4. So you want an open circle at positive 3 and a closed circle at positive 4. And once you've graphed your 2 points, you can go ahead and connect them with a line and do that once more for your last linear equation. It's f of x equals 6 if 4 is less than x is less than or equal to 5. So your horizontal line in this case would be y equals 6, which would be right here. And looking at your domain, it's 4 is less than x is less than or equal to 5. So you want to graph an open circle at positive 4, which would be right here, and then graph your other point at positive 5. In this case, it would be a closed circle at positive 5. Connect your points, and here is your final step function. It is a little bit of a tedious process since you have to graph all these linear functions and all of their domains, but once you get the hang of it, it should go a little bit quicker. Now we're going to work with a word problem. You rent a karaoke machine for 5 days. The rental company charges $50 for the first day and $25 for each additional day. Write and graph a step function that represents the relationship between the number of days, x, and the total cost of renting the karaoke machine. So to break this down, we want to make a step function, meaning we're going to write a piecewise function. Remember, a piecewise function is f of x equals or y equals to this curly bracket called a brace, and inside you'll have 2 or more linear equations. Now to write your step function, it would be a good idea to try and organize the information you're given. I went ahead and put it into a table. So looking at our problem, we know that y is going to equal to the total cost of renting the karaoke machine. And so we want a constant value that's going to be set to y that equals that total cost, but we also want to represent the relationship between the number of days x. So this relationship is actually going to be your domain, and then your constant value is going to be the total cost. And that's how you're going to get your linear equations for your step function. Right now that might seem a little bit confusing, but I'll go ahead and I'll explain how I got these values. So looking at our information, we know that we're going to rent a karaoke machine for 5 days. So we want to write a relationship for x until x hits 5. And the rental company charges $50 for the first day and $25 for each additional day. So for the first day, to represent your relationship between the number of days, as long as x is greater than 0 days, but it's less than or equal to 1 day, your total cost is going to equal to 50. And now as you keep progressing, if your total number of days is greater than 1, it's no longer to be $50, but as long as it's less than or equal to 2 days, you now add a $25 fee for your additional day. And so that's how you get your $75 for the total cost. And now you can continue this pattern until you hit 5 days. So from $75, if we rent it for greater than 2 days, but as long as it's less than or equal to 3 days, we know that we're going to have to add another $25 for that additional day, and we'll get $100. From there, if we're renting it for more than 3 days, but as long as it's less than or equal to 4 days, we add another $25 and get $125, and do that once more until you hit your 5 days. So we're renting it for greater than 4 days, but it's less than or equal to 5 days. That's an additional day fee. So your final constant value will be $150. And now that you have all your constant values and their domains, you can go ahead and make this into a step function. The step function will look something like this, and from there you can go ahead and graph it on your coordinate plane. I'm going to start with the very first linear equation, f of x equals 50. You can also just write it as y equals 50. And so we know we're going to have a horizontal line here where y equals 50, but you only want to graph it at this domain. So we have 0 is less than x is less than or equal to 1. So you want to have an open circle where x equals to 0, so that would be right here. And then for your other point, x is less than or equal to 1, you're going to have a closed circle where x equals 1. So there would be your other point. And now you can go ahead and connect your 2 points with your horizontal line. And here is your first linear equation graphed. And from there you can go ahead and continue. For the next linear equation, we have y equals to 75 if 1 is less than x is less than or equal to 2. So I know we want our horizontal line here at 75, but we only want to graph it where 1 is less than x is less than or equal to 2. So you know you want to have an open circle at positive 1, and then a closed circle at positive 2. And once you've graphed your points, you can go ahead and connect them with your horizontal line, and move on to y equals 100. So we know we want our horizontal line here at 100, but our domain is 2 is less than x is less than or equal to 3. So you want an open circle at 2 and a closed circle at positive 3. So this is how it would look like. And connect your 2 points. Do the same for y equals 125. Our horizontal line is going to be here at 125 on the y-axis, but we only want it when 3 is less than x is less than or equal to 4. So you want your open circle where x equals to 3, so that would be right here. And then you want a closed circle where x is equal to 4. And once you apply your points, go ahead and connect them. And do that for your very last linear equation, y equals 150. Horizontal line will be here at 150. Our domain is 4 is less than x is less than or equal to 5. So you want an open circle at positive 4, closed circle at positive 5 on the x-axis, and connect them. And here is your final step function written and graphed. Now we're going to move on to the very last special function, which are absolute value functions. An absolute value function has a V-shaped graph that either opens up or down, and this is how it would look like here on the right. The most basic absolute value function is f of x equals to the absolute value of x, and that is actually what's graphed here on our coordinate plane. And what I recommend is you try and remember just the general ordered pairs for your most basic absolute value function, which again is this right here. So your vertex is always going to be at 0, 0 for your most basic absolute value function. And then since it is symmetrical, however many units you go left or right from the vertex, you're going to have the same units going up. So if you go 1 unit left, you're going to go 1 unit up. And if you go 1 unit right from the vertex, you're also going 1 unit up. And so you can keep continuing that. If you go 2 units left, you go 2 units up, 2 units right, you go 2 units up. And I recommend that you try to keep that basic pattern in mind, since it'll be really helpful once you start doing translations. Remember that the absolute value of a number is always non-negative, meaning that it's always going to be positive. So the range of f of x equals to the absolute value of x is y is greater than or equal to 0, since you can't have an absolute value of a number that's negative. And the domain is always going to be all real numbers, meaning that you can plug in any real number for x and you'll get a corresponding output value. Now here is a general guide to translations when it comes to absolute value functions, and some of this information can be applied to a bunch of other different functions, so I do recommend that you try and get to know this, since it'll definitely be useful in the future. Now your most basic absolute value function is y equals to the absolute value of x, but you'll see that they're going to start adding some things called translations that are going to change how your graph looks. So sometimes there's this number in front of your absolute value symbols, and we assign the variable a. Generally, when a is greater than 0, meaning that it's positive, the graph is always going to open up, and if a is less than 0 or a is negative, the graph will open down. When it opens down, it'll look something like this. If a is between 0 and 1, meaning that it's a fraction, if you have a fraction value for your a value, it's going to make your graph look wider. And if a is greater than 1, like 2, 3, 4, and onwards, it's going to make your graph look narrower. I would think of a as the slope, so follow however many units you go up or down. And what that means is, remember your general pattern where if you go 1 unit left or right from the vertex, you're going to go the same units up for both sides. So in this case, if you go 1 unit left, you go 1 unit up, and 1 unit right, you go 1 unit up too. If you have a different number other than 1 as your a value, like 2 for example, that's going to change however many units you're going to go up. So in this case, if you go 1 unit left, you're going to go 2 units up. You want to multiply the number of ups that you usually take by your a value. And that's why I think knowing the basic pattern of a absolute value function is really helpful. So if you were to have an a value of 2 once again, and you were going to go 2 units left and 2 units right, normally in the basic pattern you're going 2 units up, but since your a value is 2, you want to multiply the number of ups that you usually take by your a value. So 2 times 2 would be 4, so now the number of units that you're going to go up is going to be 4. And so this might seem a little bit confusing right now, but you'll see how it comes together once we do a few examples. And now moving on to your k values. You might have a value that's being added outside of your absolute value symbols, and we assign that value the variable k. So if you have plus k, that means you're going to go up however many units. For example, if you have plus 4, you want to bring all your points up 4 units. And if you have minus k, that means you're going to go down k units. For example, if you have minus 4, then you want to bring all your points 4 units down. Now, looking inside your absolute value symbols, x minus h, if you have a minus h, that means that you're going to translate all your points h units right. So for example, if you have x minus 4, you want to translate all your points 4 units to the right. And if you have x plus h, that means you want to translate all your points however many units to the left. And lastly, for your vertex, if you're putting a bunch of different translations into your absolute value function, your vertex will change. So the basic format is HK. And so you want to take the h value and the k value. In the case that you don't have an h or k value in your absolute value function, that just means that your vertex is at 0, 0. Now let's say you have an equation like y equals 2, absolute value x minus 2, absolute value plus 3. To find your vertex, remember you need your h and k values. So your vertex is going to be in the format hk. Your h value is going to be the one that is either being added or subtracted from x within your absolute value signs. So in this case, it's this -2 right here. And your k value is going to be whatever is added or subtracted outside your absolute value signs, and that would be +3. Remember, you need to change the sign for h. So rather than -2, we're going to put +2 for h, but keep the sign for your k value. So that would still stay +3. The way I like to remember it is that k stands for keep. And so this is a general guide to translations in a lot of different graphs that you'll encounter later on in Algebra 1. So let's go ahead and look at our first example. We're going to graph this function and then compare the graph to the graph of y equals absolute value of x, then describe the domain and range. So our equation here is y equals absolute value of x plus 3. Keeping in mind our general guide to translations, remember that whenever you're adding or subtracting a value outside of the absolute value, then that means you're doing a vertical translation up or down. In this case, we're adding, so that means we're going to go up however many units. So we're adding 3 units to absolute value of x, and so that means we're going to translate all of our points up 3 units. So what's helpful is to first graph your parent function. So it's a good thing to try and just keep in mind and memorize the parent function points or ordered pairs. So remember that your vertex would be at 0, 0, and then from there you would have -1, 1, 1, 1, and then -2, 2, and 2, 2. And then you can go ahead and just connect those points with your 2 lines. And from there, it's much more easier to go ahead and do all your translations. Your translation in this problem is going to be up 3 units. So all you have to do is take all the points of your original function and translate them up 3 units. So for example, -2, 2, if you bring it up 3 units, would be -2, 5. -1, 1 would go up to -1, 4. 0, 0 goes up to 0, 3. 1, 1 goes up to 1, 4. And finally, 2, 2 would go up to 2, 5. And now you can plot all those points. And from there, you just connect them with your lines. Now, alternatively, you could go ahead and do a table of values. So you can just plug in the standard set of -2, -1, 0, 1, 2 for your x values. And if you were to do that, you would have -2 in for your x value. The absolute value of -2 is +2, and then +3 would give you 5. And you can go ahead and do that for all your points until you get a good set of ordered pairs to plot. So those are 2 ways you can go about graphing absolute value functions, but it's all up to whatever you prefer. Now, whenever they ask you to compare the graph to the graph of y equals absolute value of x, they just want you to write a short sentence of how it has changed. And we actually identified this earlier on. We know that the graph of y equals absolute value x plus 3 is a translation 3 units up of the graph of y equals absolute value of x. And for the last portion of this problem, they want us to describe the domain and range. As for domain, remember that domain refers to all the x values that you can plug into your equation. For absolute value functions, your domain is always going to be all real numbers, meaning that you can plug in any real number into your x of your absolute value function, and it gives you another value for you to plot. And as for range, you want to look at how your points are in relation to your y-axis. So for y equals absolute value of x plus 3, we see here that the lowest point on the y-axis is at positive 3, and from there all your y values are going up. So that means it's either y is greater than or equal to 3 for your range. And the reason why you have greater than or equal to is because your 3 is included in your range. And so now we can go ahead and move into our next problem. It's just another graphing one, except now we have a different translation. We have y equals absolute value x minus 2. Now what's different about this one is that the translation is actually inside of our absolute value signs rather than outside like the last problem. Now if you recall the general guidelines for graphing and translations, whenever you're adding or subtracting a value inside the absolute value signs, that means it's a horizontal translation, either left or right. And whenever it's subtracting, that means that you're going to do a translation to the right. And vice versa, if you have plus 2, that would be 2 units to the left. In this case, since it's minus 2, we know we're going to translate all our points right to units. And just like the last problem, we're going to compare it to the original graph and also describe the domain and range. And so for the first part, let's go ahead and just graph our parent function so that we can do our translation. Remember that your original function or parent function is going to be y equals absolute value x. The points for that are 0, 0, negative 1, 1, 1, 1, negative 2, 2, and then 2, 2. And you can go ahead and connect those with your lines. And from there, let's go ahead and do our translation. So we're going to translate all our points right to units. So for example, our vertex at 0, 0 is going to be translated 2 units to 2, 0. Then we have negative 1, 1. That will be translated to 1, 1. 1, 1 would be translated to 3, 1. Negative 2, 2 would be translated to 0, 2. And 2, 2 would be translated to 4, 2. So you can go ahead and graph those points and then connect them with your lines. And so here's how your translated graph would look like. And also, I just wanted to make a brief note on the vertex. You can actually find the vertex right away if you just look at your HK values. So remember, your H value is whatever is being added or subtracted within the absolute value signs, and then K would be whatever is being added or subtracted outside of your absolute value signs. In this case, there is nothing being added or subtracted outside, so we know our K is just going to be 0. But as for H, we have negative 2. But remember, you want to change the sign of H. So rather than negative 2, we would have positive 2. So this would be positive 2, 0, and that's where our vertex is right here. You can also use a table of values if that's what you prefer. My quick tip for a table of values is to first identify your vertex. Remember that we said it was 2, 0. And from there, you can choose more convenient points so that you get the entire graph. So I would recommend choosing like 2 points to the left of the vertex and then 2 points to the right of the vertex. So I chose 0, 1, 2, 3, 4. However, if you were only to choose the standard set of -2, -1, 0, 1, 2, notice that your vertex is at 2, so you would actually only be getting this left side of your graph. So make sure you're trying to find your vertex first so that you can get a convenient set of points. But now that we've done that, let's go ahead and compare it to the graph of y equals the absolute value of x. This is pretty simple. Remember, we identified our translation earlier and it was right 2 units. So all you have to say is that the graph of y equals the absolute value of x minus 2 is a translation 2 units to the right of the graph of y equals absolute value of x. As for your domain, remember for absolute value functions, it's always going to be all real numbers. And for your range, go ahead and look at your vertex and see where your y values are from there. In this case, we're only going up from y equals 0, so that means that our range is going to be y is greater than or equal to 0, and again, it's going to be greater than or equal to since we're including 0 for our y-axis, and then anything that is greater than 0. And that's it for that problem. We can go ahead and move on to this example. Now this one looks a little bit different since we're multiplying a value by our absolute value, x, and we also happen to have a negative sign. So we're going to graph y equals -1/2 absolute value x. Now if you recall from the general guidelines to translations, whenever you are multiplying your absolute value by a value that is between 0 and 1, it's actually going to make your graph wider. And if you're also multiplying it by a negative value, it's going to make your graph go down. So I'll go ahead and show you how to graph this. First, let's identify our vertex. For any translation, it's very helpful to first just find your center point, aka your vertex. In this case, we're looking for hk, but as we see here, there's no value that's being added or subtracted within the absolute value signs, and neither is there anything being added or subtracted outside. So we know our vertex is just going to stay at 0, 0. And so I'm going to go ahead and first graph our parent function, and from there, and we can work on our translation from there. So remember our original equation is going to be y equals absolute value x, and that would be 0, 0, -1, 1, 1, 1, -2, 2, and then 2, 2. Connect your points with your lines. And from there, let's go ahead and work on graphing our translation. So whenever you're multiplying a value outside of your absolute value sign, it can almost be thought of as slope. In this case, slope in the way that you're trying to determine however many units you're going up or down. Since we do have a negative sign, that means that we're going to go down however many units rather than up. And the 1/2 means that we're going to multiply the number of times that we usually go up by 1/2. So that might seem a little bit confusing right now, but I'll go ahead and show you how it works. Remember, our vertex is still at 0, 0, and now we can go 1 unit to the left. However, this is where our translations come into play. Remember that it's -1/2, so rather than going up 1 unit, we want to go down, but since it is being multiplied by 1/2, we want to cut our going up 1 unit into half. So rather than going up 1, you're only going to go down 1/2 units. And so you can go ahead and plot your point there. You can do the same for 1 to the right. You're going to go down 1/2 units, and then plot your other point. And now you can do the same for going left 2 units. Normally when we go left 2 units for our original function, you're going up 2 units. But remember, this is -1/2, So you're going to go down half of those 2 units, so that means you're going down 1 unit. You can go ahead and plot your point right there. And if you go 2 units to the right, rather than going up 2 units, you're going to go down 1 unit. And there is your other point. And now you can go ahead and connect all the points that you've plotted. And as we see here, our points are actually much wider, or our graph is much wider, and it's facing down rather than upward. And that's what we were talking about earlier when we were first looking at the equation. Now, if trying to just think of all these translations and trying to apply it to the original graph is a little bit confusing, please feel free to use a table of values. Again, the number one thing you want to do is just first identify your vertex. Remember, we said that it still stays at 0, 0, and then choose 2 points to the left of the vertex, 2 units to the right, and just plug it into your function and you'll get your corresponding y values. And you'll see here that even as we plug it in as a table of values, we still get the same exact ordered pairs that we were using earlier when we were using the translation method. And so now we can go ahead and do the last 3 parts. First, we want to compare the graph. So we identified that earlier. We said that the graph of y equals negative 1/2 absolute value x opens down and is wider than the graph of y equals absolute value of x. Remember, your domain is going to remain all real numbers. As for your range, it's going to be a little bit different. You want to look at your vertex. In this case, it's at 0 on the y-axis. And from there, all your y values are going down. And so your final range is going to be y is less than or equal to 0, meaning that your range includes the value 0 and anything that is less than 0. Here is our next problem. Whenever you're multiplying a value outside of your absolute value sign, it can almost be thought of as slope. In this case, slope in the way that you're trying to determine however many units you're going up or down. Since we do have a negative sign, that means that we're going to go down however many units rather than up. And the 1/2 means that we're going to multiply the number of times that we usually go up by 1/2. So that might seem a little bit confusing right now, but I'll go ahead and show you how it works. Remember, our vertex is still at 0, 0, and now we can go 1 unit to the left. However, this is where our translations come into play. Remember that it's negative 1/2, so rather than going up 1 unit, we want to go down. But since it is being multiplied by 1/2, we want to cut our going up 1 unit into half. So rather than going up 1, you're only going to go down 1/2 units. And so you can go ahead and plot your point there. You can do the same for 1 to the right. You're going to go down 1/2 units and then plot your other point. And now you can do the same for going left 2 units. Normally when we go left 2 units for our original function, you're going up 2 units. But remember, this is negative 1/2. So you're going to go down half of those 2 units. So that means you're going down 1 unit. You can go ahead and plot your point right there. And if you go 2 units to the right, rather than going up 2 units, you're going to go down 1 unit. And there is your other point. And now you can go ahead and connect all the points that you've plotted. And as we see here, our points are actually much wider, or our graph is much wider, and it's facing down rather than upward. And that's what we were talking about earlier when we were first looking at the equation. Now, if trying to just think of all these translations and trying to apply it to the original graph is a little bit confusing, please feel free to use a table of values. Again, the number one thing you want to do is just first identify your vertex. Remember we said that it still stays at 0, 0, and then choose 2 points to the left of the vertex, 2 units to the right, and just plug it into your function and you'll get your corresponding y values. And you'll see here that even as we plug it in as a table of values, we still get the same exact ordered pairs that we were using earlier when we were using the translation method. And so now we can go ahead and do the last 3 parts. First, we want to compare the graph. So we identified that earlier. We said that the graph of y equals negative 1/2 absolute value x opens down and is wider than the graph of y equals absolute value of x. Remember, your domain is going to remain all real numbers. As for your range, it's going to be a little bit different. You want to look at your vertex. In this case, it's at 0 on the y-axis, and from there all your y values are going down. And so your final range is going to be y is less than or equal to 0, meaning that your range includes the value 0 and anything that is less than 0. Now let's graph the equation y equals negative absolute value x minus 5 plus 1. Now this one looks a little bit crazy since you do have multiple translations. And whenever you do see that you have more than one translation, a good practice is to first find your vertex just so that you can see where your graph is lying. So remember that your vertex is HK, and you want to change the sign of H, so rather than negative 5, it's going to be positive 5, and keep the sign of K, so your K value will be 1, so you know your vertex is going to be at 5, 1, and I'll go ahead and plot that on our graph. And now you can go ahead and plot the remainder of your points. So once you've found your vertex, you can go ahead and look at what pattern you're going to be plotting your points. In this case, you want to look at what your absolute value function is being multiplied by. In this case, it's negative 1. Remember, you want to think of the value that it's being multiplied by as the slope and the way of how many units you're going to go up or down. So let's say that you're going 1 unit to the left. Since it is negative 1, you know that you're going to go down 1 unit. And so you want to multiply your general pattern by negative 1. So if you go 1 unit to the left, rather than going up 1 unit, you want to go down 1 unit. And same for if you go 1 unit to the right. And then you can go ahead and plot those 2 points. And same goes if you wanted to go 2 units to the left. Rather than going up 2 units, you're going to go down 2 units. And that would be your 4th point right there. 3 points would actually be enough to graph our function, but you have to make sure that those 3 points are the vertex, and then at least 1 point to the left and to the right of the vertex. And from there you can just go ahead and connect them with a line. And now that we've finished our graph, we can go ahead and describe the translation and also the domain and range. But first, if you wanted to alternatively do a table of values, you could. It does get a little bit confusing when you're dealing with a bunch of translations. So again, the general tip is just to first identify your vertex, which was 5, 1, and then choose 2 points to the left and to the right of the vertex. And from there, you just plug it into your equation and find the corresponding y values. Then you have a set of ordered pairs that you can directly plot onto your graph. Now we can do the last part of our problem, which is to describe the translation and also find the domain and range. So looking at our equation, we know that the graph of y equals negative absolute value x minus 5 plus 1 is first going to open downward, and it's going to be a translation of 5 units to the right, as we see on our graph right here, and also 1 unit up. You can actually start the problem by writing the description for how it's translated just by looking at your equation. Remember that whenever you're adding or subtracting a value within your absolute value signs, it's going to be a horizontal translation either to the left or to the right. And when you're adding or subtracting a value outside of your absolute value signs, it's going to be a vertical translation, either one unit up or 1 unit down, depending on the sign. And so we know that it's going to be a translation 5 units to the right, a translation 1 unit up of y equals absolute value x. And as for the domain, remember that for absolute value functions, that's going to be all real numbers. And for your range, that corresponds to all your y values. First look at your vertex, and so our vertex is at +1 on the y-axis, and from there all our y values are going down and are less than +1. So your final range is going to be y is less than or equal to 1. Here is our very last example. We're going to be graphing y equals 4, absolute value x minus 4. Now remember, whenever you have multiple translations, it's pretty helpful to first identify your vertex. It's going to be hk. In this case, we don't have an h value, so that would just be 0, and our k is going to be -4. So we know that our vertex is going to be here at 0, -4, and that reflects that translation 4 units down. So you see that our vertex is going 4 units down. And from there, we can go ahead and start graphing our other points. Let's look at our other translation. We see here that we're multiplying our absolute value function by 4. Again, think of this as your slope. And in the way that you're trying to find how many units you're going to be going up. So if you follow the general pattern of going 1 unit to the left from your vertex, which in this case is at 0, -4, and you go up 1 unit, since you're multiplying it by 4, you actually want to multiply however many units you're going up by 4. So in this case, rather than going 1 unit left and 1 unit up, you're going to go 1 unit left and 4 units up, since you're multiplying your 1 unit by 4. And do the same for going 1 unit to the right. You're going to go 4 units up, and there is your second point. Now if you were to go 2 units to the left, normally you would go 2 units up, but you're multiplying it by 4, so then you would make it 8 units up. And so your point would be right here. Same if you go 2 units to the right. And of course, alternatively, if you're not feeling too comfortable graphing just by using the translations you're given, you can go ahead and use a table of values. Again, just first identify your vertex. Again, it was 0, -4. Choose 2 x values to the left and 2 x values to the right, and then plug them into your equation, and then get your corresponding y values. And you'll find that you have ordered pairs that you can directly graph onto your coordinate plane, and then just connect with your 2 lines. But now that we have our translated graph, I'm going to go ahead and compare it to our original graph of y equals absolute value of x. So we know that the graph of y equals 4, absolute value x plus 4, is narrower and is a translation 4 units down of y equals absolute value x. Now just a side note, whenever you're multiplying your absolute value by any value that is greater than 1, then it's actually going to make your graph narrower, as we see here in this example. As for your domain, it's going to be all real numbers, and for your range, look at your vertex, and it's at -4 on the y-axis, and from your vertex it's actually going up to values that are greater than -4. So we know that all your y values are going to be y is greater than or equal to -4, and there is your range. That is it for today's video. Thank you so much for watching. I hope you learned something new. If you have any questions about the problems that I do in these videos, please feel free to reach out at kaelin.david24@gmail.com. As always, all information regarding tutoring, lesson requests, and additional practice will be linked below down in the description box.